Number 1, find the 4 solutions to x to the 4th minus 1 equals 0. So when we solve polynomial equations, we factor. So x to the 4th minus 1. Well, that's the difference of perfect squares. That's x squared minus 1 times x squared plus 1 equals 0. X squared minus 1 is the difference of perfect squares again, so that's x minus 1, x plus 1. Then x squared plus 1. In 9th grade, we would say we can't factor that, but now that we have the complex numbers, we do. We treat it as if it was difference of perfect squares, so that's x plus 1i, x minus 1i, because that's really x squared minus negative 1. Well, that's x. What's the square root of negative 1? The square root of negative 1 is I, so that's where that identity comes from. Equals 0, so I get x equals 1. X equals negative 1, x equals negative I, x equals positive I. Those are my 4 solutions to that polynomial equation. Find all solutions to this equation. Well, there's 4 terms, so I'm probably grouping. Is there a GCF? No. So let's group. Take out a 4x squared. What am I left with? Left with x minus 3. Then I take out from here plus 25, and I'm left with x minus 3. Well, they have that common factor of x minus 3, so let's factor that out. That's my new GCF, and I'm left with 4x squared plus 25 equals 0. 4x squared plus 25 is the sum of perfect squares, so I need to use complex numbers to factor this. If this was the difference of perfect squares, we would say 2x plus minus, but that's not 5 and 5, it's 5i and minus 5i, because that's the sum of perfect squares. And now we solve these equations. X minus 3 equals 0 tells me x equals 3. 2x plus 5i equals 0. Well, 2x equals negative 5i. Divide by 2. We get x equals minus 5i over 2. That's a solution. And I know they come in conjugate pairs, so this better be the conjugate of that. 2x minus 5i equals 0. Add that over, get 2x equals 5i. So x equals 5i over 2. So my solutions are 3, and then plus or minus 5i over 2. You don't have to write them like that, but those are my 3 solutions to this 3rd degree polynomial equation. Whenever we see the sum of perfect squares, we can factor it if we need to by factoring it over the complex numbers. This is really helpful when solving polynomial equations. Find the solutions to x squared minus 6x plus 10 equals 0. Use these solutions to write x squared minus 6x plus 10 as the product of linear factors. So first let's solve that equation. What multiplies to 10 that adds to 6, negative 6? Nothing. There's no integers that do that, so we have to use the quadratic formula. Or you could complete the square. This is actually one where completing the square wouldn't be terrible. It's probably actually quicker, but we don't remember completing the square from 9th grade. So let's go quad formula. A is 1, B is negative 6, C is 10. So B squared, 36 minus 4 times 1 times 10. 36 minus 40 is negative 4. So my discriminant is negative 4, which tells me I have complex solutions. X equals negative b, 6, plus or minus the square root of the discriminant, all over 2a, all over 2. So I got x equals 6 divided by 2 is 3, plus or minus radical negative 4 is I radical 4, 2i, plus or minus 2i over 2. So x equals, because I distributed the division there, 3 plus or minus I. So one solution is 3 plus I, the other solution is the conjugate 3 minus I. Well, if those are my zeros, what factors did those come from? Now I can factor that. I can factor that expression as x minus 3 plus I. And then the factor, if that's my 0, 3 minus I get x minus 3 minus I. And we can leave it like that. But this, the product of those two linear factors, gives me back x squared minus 6x plus 10, using that relationship between zeros and factors again. This time, the numbers are not nice integers, they are complex numbers. Number 4, find the solutions to x to the fourth minus 12x squared plus 20 equals 0. So this looks kind of quadratic, but in the first term of my factors are going to be x squared, and I'm factoring it because I'm solving a polynomial equation. What multiplies to 20 that adds to negative 12? What multiplies to 20 that adds to negative 12? Well, minus 10 and minus 2. Well, these don't look like the difference of perfect squares, but I know I can factor that as x minus radical 10 times x plus radical 10, because radical 10 times radical 10 is 10. And then this factors as x minus radical 2 times x plus radical 2 equals 0. So this gives me the zeros of x equals radical 10, x equals negative radical 10, x equals radical 2, and x equals negative radical 2. Those are my 4 solutions. You might see that written as x equals plus or minus radical 10, and x equals plus or minus radical 2, but those are my 4 solutions. It doesn't look like the difference of perfect squares, but we can treat it as if it was the difference of perfect squares. 5. Write an equation for a polynomial with the zeros of 3, 2 minus 5i, and 2 plus 5i. So if I have a 0 of 3, that means I have a factor of x minus 3. If I have a 0 of 2 minus 5i, I have a factor of x minus 2 minus 5i. And I know complex numbers come in conjugate pairs when they're solutions. So 2 plus 5i also has to be a solution. So I get x minus 2 plus 5i. If I wanted to expand this out, I could. If I wanted to, I'd just have to do a lot of multiplying. I'd have to do a lot of multiplying and do x minus 3 times x minus 2 plus 5i, and then x minus 2 minus 5i. I can use a 3 by 3 table to multiply these two together, and then I'll multiply it by that, x minus 2 plus 5i, x minus 2 minus 5i. Based on the structure of these conjugate pairs, we're actually going to end up with a nice quadratic. It's just going to be a little bit messy to get there. X times x is x squared, minus 2x, plus 5ix, minus 2x, minus 2 times minus 2 is 4, 5i times negative 2 is negative 10i, x times negative 5i is negative 5ix, negative 2 times negative 10i is times negative 5i is positive 10i, 5i times negative 5i is negative 25i squared. That seems like a lot, but nice things are going to happen here. 5ix minus 5ix, those add to 0. Minus 10i, 10i, those add to 0. And I know that I squared is negative 1, so negative 25i squared is really negative 25 times negative 1, which is 25. So after I multiply these together, I end up with x squared times, x squared, not times, x squared plus negative 4x, 4 and 25 plus 29. 29. So that's the product of those two, and I have to multiply that by x minus 3. And I could do that, but I'm going to save ourselves some time here. You can make a table, and I know you can all distribute that in to get a polynomial in standard form. Notice that it didn't say in standard form, so I am fine with this answer here. I'm fine with that answer there because it didn't mention standard form at all. 6. If 2 plus 4i is a solution to a quadratic equation, what's the other solution? Well, solutions come in conjugate pairs for complex numbers. So if I have 2 plus 4i, 2 minus 4i is also a solution. Find the equation of a quadratic with these solutions. Well, if these are my zeros, my factors are x minus 2 plus 4i and x minus 2 minus 4i. I could distribute that negative 1 in. X minus 2 minus 4i times x minus 2 plus 4i. And then you can make that 3 by 3 table like I did on that previous question to get the answer in standard form, or you can be sneaky here and look for and make use of structure. If I group those two together, I have something minus 4i, something plus 4i. This is the difference of perfect squares. That's x minus 2 squared minus 4i squared. Now, how many of you noticed that? Probably not many of you, but that's always going to happen when you have these complex zeros. And again, this is not a big idea at all. The big idea is that 2 minus 4i is also a solution, and those are your factors. Don't worry about this next step because you really could have just multiplied it out. I'm just saving some time. So I have x squared minus 2 minus 4x plus 4 minus 16i squared. And I know that 16i squared is really, well, what's I squared? We know that I squared is negative 1, so negative 16 times negative 1 is positive 16. So I get x squared minus 4x plus 4 plus 16. So my final answer is x squared minus 4x plus 20. That's my final answer.